Hello, and thank you for attending our presentation. Today we will be talking about reinforcement learning for Snake. So, we developed a video game clone of the original Snake game. Here, the player or agent must target collectibles while avoiding its tail and the boundaries of the environment. A-star pathfinding was used as an example of how the agent can play the game imperatively by being told what to do. We then implemented various reinforcement learning techniques to expand on this, demonstrating how the agent can learn how to play the game by itself. For A-star pathfinding, we used Aaron Granberg's Unity implementation. Here the game environment was subdivided into units. From these units, paths were calculated, taking into consideration obstacles. These paths were calculated as the shortest possible routes with respect to the Euclidean distance metric. Each path was calculated every 0.1 seconds, since the environment was dynamic and changing frequently. The agent is able to play the game pretty well, but due to a discrete set of actions, it starts failing when it comes to avoiding its body parts and the boundaries. This can be improved with a method where the agent learns from its actions, and such is the case for reinforcement learning.
The first reinforcement algorithm that was taken into consideration was the Q-Learning algorithm that was developed by Watkins in 1989. This algorithm makes use of the Markov decision process to estimate the environment and make use of that estimation to model the agent's action. QLearning makes use of a Q-table in which each possible state action is stored based on the reward function. A reward is defined as the goal of the agent. Doing a positive action will result in a positive reward, while on the other hand, doing a negative action will result in a negative reward. The agent is to always choose the action that will maximize the reward obtained. Q-learning requires a balancing strategy between exploration and exploitation. The exploration phase results in the agent exploring the environment and populating the Q-table by performing trial and error actions, while on the other hand, the exploration phase is when the agent starts performing informed decisions based on what is found in the Q-table. For the game of snakes, the states are being defined as the position of the agent's head in relation to the position of the food, taking the x and y difference of the coordinates between the two locations. The direction to which the snake should move is being defined by the positive or negative sign. Having a negative sign before the x value implies that the food is to the left of the agent, while having a negative sign before the y value implies that the food is below the agent. The agent will receive an award when the snake finds and eats the food. On the other hand, the agent is to receive a negative reward when the snake hits the boundaries or when the snake hits itself. After numerous experimentations, it was concluded that the Q-learning algorithm did not show promising results for the game of Snake. This could be due to a number of contributing factors. The first factor revolves around the huge number of states. As Watkins stated in his research in 1992, Q-learning converges to the optimal Q values as long as all the actions are repeatedly sampled in all the states. Therefore, for this to happen, a long training time is required. In addition, the agent is learning about the location of the bounding walls and the body explicitly, since no information regarding these locations are being stored in the Q-table. The agent is also not learning to take the shortest path towards the food, as there are no negative rewards associated with every extra step the snake does. The algorithm can also be unpredictable. The agent during the exploration phase can get lucky and start finding the food quicker, causing the Q-table to be populated with more fine-tuned data more quickly.
The second reinforcement learning algorithm implemented is the SARSA algorithm. This algorithm works in a similar way to the Q-learning algorithm, in which it makes use of the Markov decision-making process as well as a greedy policy when making decisions so as to achieve a balance between exploration and exploitation. the reward is calculated in the same way. SARSA, however, makes use of an OnPolicy algorithm, allowing for the next action to be taken to be decided upon by the current action. This means that given the current state and action, the reward observed by these, and the next desired state, the algorithm is able to identify the next best action to be taken. Unlike the QLearning algorithm, which enters a new value to its Q table once a new state-action pair has been encountered, the SARSA algorithm makes use of a Q table with a predetermined size and dimension, and simply updates the value in the table with each pair encountered. The results obtained by the SARSA algorithm when carried out on the game of Snake after multiple iterations were not ideal. However, due to the fact that the SARSA algorithm is able to learn to avoid a negative action so as to not cause harm to the agent, a large negative reward is seen to result in a more promising outcome. The suboptimal results obtained may be due to a number of contributing factors, most of which are similar to that of QLearning. The large environment space implemented results in a sizable number of possible states for the agent to explore. This means that even after an immense amount of iterations, a great number of states have still yet not even been encountered, resulting in a long training time. The algorithm also requires a large memory space from the start of the game due to the predetermined Q table, as opposed to QLearning, where the size increases as the game is played.
Proximal Policy Optimization, commonly known as PPO, is a reinforcement learning technique engineered by Schulman et al. In 2017. In training, it includes neural networks that maps the agent's current observations to the action it can take with the best policy. In training, weights of the neural network are influenced by the actions of the agent, which make the environment indicate positive or negative reinforcement. At each step, costly errors in the neural network are minimized, but they're also minimized in such a way that there isn't a huge deviation from the policy of the previous step. This avoids overfitting. To implement PPO, we use the ML Agents Toolkit, which is an intuitive machine learning toolkit for Unity. It allowed us to train multiple instances of the game for faster training times, as well as 3 options for types of observations. All options for observations were implemented, and these included vector-based, CNN-based, and raycasting-based observations. A vector-based approach consisted of vector observations, which focused on positions of entities within the game environment. Such entities included the collectible, the agent, the grid direction in which the agent is facing, the upper border, the bottom border, the left border, and finally the right border of the game environment. Vector observations of the borders were not included initially, but after being included, they were actually seen to improve the results. In the x-axis of these graphs, we have the number of actions that the agent has taken during training. Meanwhile, in the y-axis, we have cumulative reward and episode length, respectively. Training consisted of a number of episodes, and each episode was defined to end on either when the agent reached the collectible or it bumped into an obstacle. In fact, looking at the graphs, we see that the blue line representing with border observations is able to achieve a shorter episode length than without. This indicates that it was able to learn shorter paths. Meanwhile, the cumulative reward was the average reward calculated from all previous episodes. Whenever the agent successfully reached a collectible, the episode was ended with a reward of 1. Otherwise, when it bumped into an obstacle, it was ended with a reward of 0. This promoted positive reinforcement over negative reinforcement, as it was in fact found to behave better, to learn better with positive reinforcement alone than positive reinforcement alongside negative or just negative alone. As we can see with vector-based observations, the agent is able to play the game pretty well, but it starts to fail when it grows to a certain length. This is because none of the entities include its body parts, and vector observations of its body parts could not be included because they were dynamically increasing in count, and inputs to a neural network have to be static. They have to be defined in size at the very beginning. In attempts to solve this issue, a CNN approach was taken. Here, images were fed to a convolutional neural network at every action that the agent took. This made it so that an observation of the whole game environment was included, including its body parts. Since images are much more complex than location-based vectors, to cater for this, two experiments were approached where the images were downsampled in two different ways. The first one was a 96 by 54 resolution in grayscale, so did not have to worry about red, green, blue channels, simply just one channel for grayscale. Meanwhile, the other one was more complex. It was a 956 by 144 resolution in color, so not only was the resolution higher, but there was more complexity in the number of channels, where from 1 it went to 3. Unfortunately, for both of these downsampling experiments, none yielded conclusive results, simply because the image complexity was too high. An approach for avoiding obstacles with less of an input complexity was necessary. The next approach we tried yielded the best results, and this was raycasting. The motivation for this was also visual like CNN, but instead of a global perspective from top down, the perspective was more with respect to the agent, where rays were casted in front of it, left and right, as if it was from its own eyesight. 6 rays were casted, 3 of which were for detecting collectibles and the other 3 were for detecting body parts. When nothing is detected by a ray, its corresponding observational value is taken as 0. Meanwhile, when something is detected, observational values are taken as 1 minus the distance from the agent to the collectible over the length of the ray. We made it like this so that the observational values were within a range of 0 to 1, with values closer to 1 indicating that the obstacle was closer to the agent and that the agent was more in danger than values closer to 0. Now, 3 experiments with raycasting were approached. One was simply with just the 6 rays as observations. The other was with 6 rays and on top of that, a vector observation of the grid direction in which the agent is currently facing. And on top of that, for the third variation, walls were included in the game as a secondary obstacle form alongside the boundaries and body parts. But it also resulted in less of a cumulative reward, simply because the wall made the agent practice, it made it train in a more confined space. So the probability that an episode would end based on it hitting its tail instead of a static wall was much less. The best experiment for raycasting was when grid direction was included in the observations, as can be seen in the 2 graphs. It achieves a higher cumulative reward and an even shorter episode length, indicating shorter paths to the targets. So this is the resulting behavior of being trained with raycasting and grid direction. It is our best trained agent. As you can see, it's able to navigate the game environment, it's able to target the collectibles whilst avoiding the border and its own body parts. In comparison to the other approaches, it's able to survive for a much longer time, achieving higher scores. And that successfully concludes reinforcement learning for Snake, where the best reinforcement learning approach was Proximal Policy Optimization, with raycasting based observations alongside grid direction. Thank you so much for your attention. Now, does anyone have any questions?